Good day everybody, Zahida here with an introduction to weaves. We begin by looking at the anatomy of a weave, and much like the anatomy of the human body, a wave can be broken down into different parts. But what is a wave? A wave is a disturbance in which energy is transferred or moved from one point to another. The epicenter of an earthquake, or a ripple that transfers energy from the center outward. Grammatically, we can represent a wave as a sine or cos graph. For the purpose of this video, we will use a sine graph, where the x-axis or the horizontal axis is described or known as the equilibrium or rest position. This position is a reference position which remains fixed, and about which the vibration of particles and the direction of the wave can be attained. The highest point of a wave, or the peak of a wave, is called, from this equilibrium or reference or rest position, is called the crest. The lowest point of this wave is called a trough. The distance between both crest and trough from the equilibrium position is the same for an object or a wave that transfers the same amount of energy, and this distance is called the amplitude. The amplitude is defined as the maximum displacement from the equilibrium position to either peaks of the wave, where the peaks are either crest or troughs of a wave. As a result, the vertical axis is called the displacement axis. It should also be noted that the negative sign that represents amplitude of a trough is a mere indication of direction of where a trough is positioned, which is below the equilibrium axis. In a Cartesian plane below the x-axis or the horizontal axis, values are indicated as negative y. As a result, a trough is positioned or yields an amplitude of A that can be read off from the graph, but noted as negative on the Cartesian plane itself. Let's look at what property amplitude gives us. If the amplitude of a wave is given as A, and of course this value is hence doubled, it means that the intensity of the wave increases. What does this mean? For a water wave, you have a larger amplitude of a water wave, a larger water wave. For light, you have brighter light, and for sound, you have louder sound. So amplitude relates to loudness in terms of sound. We say that the larger the amplitude, the louder the sound. Let us now consider the two classifications of waves, transverse and longitudinal waves. Beginning with a longitudinal wave, if we hold a slinky fixed at one end and allow the other end to be pushed into it, then we will actually notice that there are regions where the slinky appears grouped together and some regions are further apart. The regions that are grouped together are actually called compression regions. Where they are spread apart, they are called rarefactions. We can attach an object on a slinky, on one ring of that slinky that is, for example, a piece of Play-Doh, or to tie a string on one ring, and observe its movement. This object would represent a particle. In observing this particle, we notice that it moves to and fro along the direction in which we are allowing that particle to move, or that slinky to move. As a result, for longitudinal waves, we say that the vibration of particles happen along the same direction as the wave is directed, or the direction of propagation of the wave. We say, therefore, therefore, that they are parallel to each other. Now, if we consider a string or rope fixed at one end and being tugged up in an upward-downward motion, we create what is called a transverse wave. With a transverse wave, the particles vibrate vertically, whereas the energy or direction of the wave still occurs horizontally. What does this mean? It means that a transverse wave is one in which the vibration of particles are at right angles or perpendicular to the direction of travel or direction of propagation of a wave. In the relation shown, the vertical arrows indicate the vibration of particles, whereas the horizontal arrows at the very top of the wave indicate the direction of energy or travel of this wave. Let's now consider the type of graphs that we can use to quantify waves. First up is displacement distance graphs, where displacement lies on the y-axis or vertical axis and distance is drawn on the x or horizontal axis. The horizontal distance between consecutive crests is actually the wavelength. The wavelength is actually defined as the distance between two successive particles which are in phase. In phase or in sync, particles lie on successive crests or successive troughs. It is important to remember that this horizontal distance is taken as wavelength and is also parallel to our horizontal axis, which is also measured in a unit of length. For SI units, this distance is taken as meters, but it can be noted as a prefix as well. It is also important to recognize that to accurately measure wavelength, the oscillating body must return to its original starting point. This can be better seen using a simple pendulum, where an entire oscillation is obtained when an object or the oscillating body returns to its original starting point. half an oscillation is completed as shown in the diagram. In returning to its original starting point, it completes an oscillation, hence return to its in-phase position. The next type of graph is a displacement time graph, where again displacement lies on the vertical axis, and in this case time lies on the horizontal axis. Using the same shape of a graph where we are considering two pulses or two complete oscillations, we can now decipher what may be relevant in a graph as such. In such a graph, as the graph before, amplitude can still be calculated. However, since the horizontal axis is now time, wavelength cannot be directly measured from this graph. Instead, the time it takes to complete one entire oscillation, as shown in the red line, is considered, or moving from point 1 to point 2, is considered to be the period of oscillation. It is also the time it takes for one complete pulse to be completed. Once again, the particle returns to the equilibrium position, which is considered to be the starting point from point 1 to point 2. One complete pulse is also called one complete cycle. The time it takes to cover a complete pulse or cycle or revolution or an oscillation is called the period of a wave or an oscillation. The symbol for period is capital T. It is a time, and the SI unit for period is seconds. It is also important to remember that such graphs may also contain prefixes of such a unit, so be aware. Now, frequency is directly related to period, in that frequency is considered to be the number of oscillations that occur in 1 second or per unit time. As a result, frequency is given as 1 divided by the period of an oscillation or a wave. The unit for frequency is per second, second to the power of -1, or hertz, named after the scientist himself. Another very useful formula is that of velocity, where velocity is given as the product of frequency of an oscillation and wavelength, which is given as the Greek alphabet, or represented as the Greek alphabet lambda. This formula is quite useful, and it can be easily represented by a simple pyramid. Here is the summary of what we have done so far, and some useful examples at the very end. Feel free to ask any questions in the comments below, and teach someone what you know.